February 2025, Hensoldt and Indra announce the Eurofighter radar Mk1 Step 1 is entering mass production, with deliveries starting in the summer of 2025. The most advanced fighter jet radar in Europe, AESA technology, active electronically scanned array. A phased array with electronic beam steering, Hensoldt is the leading German radar manufacturer. But take a look at the basic technology. Electronic beam steering without mechanical movement. This principle wasn't invented in 2025. It wasn't developed in the 1960s. Back in 1943, GEMA in Germany built the Mammut radar, FUMG 41-42, the world's first phased array radar, electronic beam steering over plus or minus 50 degrees, without moving the antenna. 82 years later, every modern radar system uses this German concept. Patriot, AEGIS, S-400, THAAD, all based on phased array technology, and the roots lie in Germany. But the story begins even earlier. 1887, Heinrich Hertz, electromagnetic waves, the foundation of everything that followed. Today, I'm going to show you 138 years of German radar technology, from Hertz to Hensoldt, the documented lineage that no one talks about. The numbers are impressive. The global radar industry is estimated at over $50 billion. Military radars, air traffic control, weather forecasting, speed measurement, ship navigation. Tens of thousands of radar systems in use worldwide. Every single one is based on principles developed in Germany. This is not an exaggeration. This is documented technical history, and it starts with a man in Karlsruhe. 1887, Heinrich Hertz, a physicist at the Karlsruhe Institute of Technology. He conducted classic experiments on electromagnetic radiation. James Clerk Maxwell had theoretically predicted that electromagnetic waves existed. Hertz proved it experimentally. He built a spark transmitter. Wavelength of 66 centimeters, about 455 megahertz. Then he showed these waves are reflected by metallic objects. Just like light, they can be focused, they can be detected. The reflection follows the same laws as optical light. That was the fundamental principle of radar. Send out electromagnetic waves, receive the reflection, determine the position and distance of the object. Hertz had no military application in mind. He was a pure scientist. But his discovery laid the foundation for a technology that would change the world. 17 years later, 1904, Chris Hülsmeyer, a German inventor from Düsseldorf. He recognized the military and commercial potential of Hertz's discovery. Hülsmeyer built the Telemobiloscope, the first working device for detecting distant metallic objects with radio waves. He demonstrated it in the port of Cologne, a ship in dense fog, invisible to the eye, but the Telemobiloscope detected it. On September 23, 1904, Hülsmeyer received a British patent for a complete radar system. It worked with a 50-centimeter wavelength, used a spark generator for pulsed radar signals. That was 1904, 35 years before World War II. Germany had invented the radar concept before most nations even understood radio technology. But Hülsmeyer was ahead of his time. The German Imperial Navy showed no interest. Commercial ship owners didn't want to buy it. The technology was too new, too unknown, too expensive. Hülsmeyer gave up. His company went bankrupt. The patents expired. The Telemobiloscope was forgotten, but the principle remained documented. German technical archives preserved the knowledge. Then came the 1920s, a crucial step in radar development, the pulsed radar system, credited to the German physicist Chris Hill. Instead of continuous waves, pulsed radar used short pulses. The advantage? Time measurement. The time between sending and receiving the reflection gives the distance. Light travels 300,000 kilometers per second. Electromagnetic waves the same. A pulse that comes back in 1 microsecond means the object is 150 meters away. This precision was revolutionary. Pulsed radar became the basis of all modern systems. 1933, Adolf Hitler comes to power. Germany begins a massive rearmament. The Wehrmacht is looking for technological advantages. Radar suddenly gets top priority. 1935, several German companies are working on radar systems. GEMA, the Society for Electroacoustic and Mechanical Devices, Lorenz, Telefunken. The competition drives innovation. Rudi Kohler at GEMA is often called the father of German radar. In May 1935, GEMA demonstrated a pulsed system. It worked. It was reliable. It was technically superior to the early British and American systems. GEMA collaborated with Lorenz on the Freya and SeaTact systems. Bill Runge, director of Telefunken's radio research laboratory, realized in the spring of 1935, radar is feasible. He started a crash program, but Lorenz was already working on early warning systems, so Telefunken focused on something else: short-range, precise target tracking for anti-aircraft guns. That became the Würzburg radar. Technically speaking, the Würzburg was brilliant. The Telefunken team developed an accurate system based on a klystron microwave tube, operating frequency 553 to 566 megahertz. That corresponds to a wavelength of 54 to 53 centimeters. Extremely short for the time, pulse length 2 microseconds, peak power 7 to 11 kilowatts, pulse repetition frequency 3750 hertz, maximum range about 29 kilometers, accuracy about 25 meters in distance and angle. The antenna, a parabolic dish, 3 meters in diameter. This precision was unprecedented. No other country had a radar with 25-meter accuracy in 1940. The system was put into service in 1940. By the end of the war, 4,000 Würzburg radars had been produced. They guided German flak batteries. At night, in fog, in bad weather, the Würzburg saw everything. British bombers learned to fear the Würzburg. German flak hit with terrifying precision. That was no luck. That was radar-guided fire based on German technology. There was also the Würzburg Riese, meaning giant, a larger version with a 7.5-meter parabolic antenna, even more precise, even greater range, but no longer mobile, too big to move. The Würzburg Riese was used for fixed air defense, coastal protection, city defense, important industrial plants. Germany covered all of Europe with a network of Würzburg radars. But Würzburg was only half of the German radar system. The other half was Freya, developed by GEMA. Freya was a 2D early warning radar. 2D means it could determine distance and direction, but not altitude. Operating wavelength, about 2.4 meters, corresponding to 125 megahertz, much longer wavelengths than Würzburg. The advantage, greater range. In December 1939, a Freya radar system detected a Royal Air Force formation at 113 kilometers distance. That was a world record. No British or American radar could do that in 1939. The German tactic combined both systems. Freya detected incoming bombers at long range, gave advance warning, alerted fighters and anti-aircraft guns. Then, when the bombers came closer, Würzburg took over. Precise target tracking, fire control for anti-aircraft, interception by night fighters. The system was integrated. This was in 1940. Germany had the world's most advanced radar-based air defense. The British knew this. That's why they organized Operation Biting in February 1942. A commando raid on a Würzburg station near Bruneval, France. British paratroopers landed, stormed the installation, dismantled components of a Würzburg A model, and escaped. The captured parts were brought to Britain. British engineers analyzed them in detail. The reports showed impression. A British technical intelligence document from 1942 notes German radar technology is, in some aspects, more advanced than our own. The accuracy of the Würzburg surpasses anything we possess. The design shows superior engineering, but Germany developed even further. 1943, GEMA, the Society for Electroacoustic and Mechanical Devices, built the Mammut radar, FUMG 4142. This was something completely new. A phased array, no mechanically moving antenna, instead electronic beam steering. The Mammut consisted of 8 or 6 Freya radar system antenna arrays, fixed mounted. The beam could be electronically steered over plus or minus 50 degrees. This was achieved through phase shifters, bypass lines in the feed line. Different phase delays between the array elements changed the direction of the main beam. No moving parts, no mechanical delay. The beam jumped electronically. That was the world's first operational phased array radar. Look at the significance. Earlier British chain-home radars used phase relationships between antenna pairs for direction finding. But Mammut was the first volume production design that used the idea. Sending and receiving through an array of individually phase-controlled elements. The principle behind every modern phased array radar, AEGIS ships, Patriot missiles, THAAD, F-35 APG-81, all use phased array. All are based on the concept that GEMA demonstrated in 1943. Of course, Mammut was primitive by today's standards, analog phase shifters instead of digital control, VHF band instead of microwaves, mechanical switches instead of semiconductors. But the concept was revolutionary. Electronic beam steering without mechanical movement. That was the breakthrough that would shape the next 80 years of radar development. Germany also had Liechtenstein, an airborne radar for night fighters, developed by Telefunken, wavelength 62 centimeters, 485 megahertz, power 1.5 kilowatts, mounted in Mi-110 and Ju-88 night fighters. German pilots hunted British bombers in the dark. No moonlight needed. The radar saw everything. The Royal Air Force suffered heavy losses until they figured out how to deceive the system with chaff, metallic strips that produced radar echoes. There was also SeaTact for German Imperial Navy ships, coastal surveillance, submarine detection. Germany built a complete radar ecosystem. Air defense, naval warfare, artillery fire control, night fighting, every area had specialized German radar systems. The technical diversity was impressive, but it had a common origin. German physics and engineering, from Hertz to GEMA, the Society for Electroacoustic and Mechanical Devices. Let's talk about the technical superiority. 1940. Germany had Würzburg with 25-meter accuracy. Great Britain had chain-home with about 5-kilometer accuracy. That's a factor of 200 difference. America had SCR 270 with about 300-meter accuracy, better than chain-home, but still far behind Würzburg. Why was Germany so far ahead? 3 reasons. First, continuous research since Hertz in 1887. Germany had 50 years of experience with electromagnetic technology. Hülsmeyer in 1904 had demonstrated the concept. The knowledge base existed. When radar became militarily important, Germany used existing expertise. Second, industrial expertise. Telefunken, Siemens, GEMA, the Society for Electroacoustic and Mechanical Devices. German electronics companies were world leaders in the 1930s. They had the manufacturing capacity. They had the engineers. They could produce complex systems. Third, military prioritization. Hitler wanted technological superiority. Radar got unlimited resources. The best scientists, the best factories, the best material. Germany invested massively. The result was a lead of several years over the Allies, but technological superiority does not guarantee a war victory. Germany lost despite better radar. Why? Because radar alone does not win wars. Strategy, resources, industry, manpower, all that counts more. Germany had better radar, but fewer aircraft, fewer pilots, less fuel. From 1943, Allied production capacities overwhelmed German technical quality, but the technology itself remained superior. And then came May 1945. Germany surrendered. The Allies marched in. Operation Paperclip in the American zone, Operation Osawavi Akim in the Soviet zone, British intelligence teams in their zone, French teams in their zone. Everyone wanted German radar technology. GEMA factories were confiscated, Telefunken production sites taken over, technical documentation confiscated, German engineers interrogated, the best recruited, Bill Runge. The Telefunken director who led the Würzburg program was interviewed by American teams. His reports on radar development were studied. Other GEMA engineers went to the Soviet Union, some voluntarily, many under coercion. Their knowledge flowed into Soviet radar programs, the same in Great Britain and France. German radar expertise was globally distributed. The technical documents were detailed. Americans captured complete sets of Würzburg blueprints. Manufacturing manuals, test protocols, maintenance instructions. They learned not only how Würzburg worked, but also the development philosophy behind it. Why were certain frequencies chosen? How was accuracy maximized? Which materials worked best? All this knowledge flowed into American post-war radar development. The Soviets sometimes copied directly. Early Soviet radars of the late 1940s show clear design similarities to German systems. The British integrated German knowledge into their own developments, the French alike. Germany lost the war, but German radar technology won. It became the basis for global development. Look at post-war developments. The 1950s, America developed the AN/FPS-16 tracking radar, precision target tracking for missile ranges. The specifications are strikingly similar to the Würzburg: parabolic antenna, high frequency, precise angular measurement. These similarities are no coincidence. American engineers studied captured Würzburg systems. They understood the principles, and they built upon them. The Soviet Union developed the P-series radars, P-8, P-12, P-14. Early versions display design elements reminiscent of the German Freya radar systems. Long wavelength for extended range, VHF band. The Soviets had access to German engineers and documentation. They utilized that knowledge. But the real revolution came in the 1960s. Phased array radars for missile defense. America developed Sentinel, later Safeguard, massive, fixed antenna arrays, electronic beam steering, thousands of individual array elements, each element controlled with phase shifters. The beam could sweep across the entire sky in microseconds. This was necessary for ICBM defense. Ballistic missiles fly too fast for mechanical antenna movement. The concept, exactly the Mammut principle from 1943. GEMA had demonstrated electronic beam steering is possible. The Americans took that concept and scaled it up. Instead of 6 Freya arrays, they used thousands of microwave elements. Instead of analog phase shifters, they used digital control. But the fundamental idea remained identical. An array of emitters. Phase control creates a directed beam. Electronic steering without mechanical movement. 1973. The USS Norton Sound tests the AEGIS radar, Spyway-1, a phased array system for naval air defense. 1 fixed antenna per ship side, 4 antennas in total for 360-degree coverage. Each antenna can track dozens of targets simultaneously. The beam jumps electronically between targets. Dwell time is only milliseconds per target, but sufficient for tracking. The system can track and prioritize 100 targets simultaneously. It can guide SM-2 missiles. AEGIS became the standard for American cruisers and destroyers. The 1980s, the Patriot Air Defense System, AN/MPQ-53 radar, again, a phased array, a mobile version, mounted on a truck trailer, 5,000 transmitter-receiver modules in the antenna, electronic beam steering over 120 degrees azimuth and 80 degrees elevation. The system can track aircraft, cruise missiles, and ballistic missiles. The Patriot has been deployed in 18 countries. The Gulf War in 1991. Iraq in 2003, currently Ukraine 2022-2025. The most widely deployed phased array surface-to-air missile system in the world. Each of these systems, AEGIS, Patriot, Safeguard, utilizes electronic beam steering. Each is a direct technological descendant of the German Mammut radar from 1943. The Americans developed it further. They perfected it. They produced it on a large scale. But the basic concept was German. Russia followed the same path. The S-300 air defense system, introduced in 1979, the 30N6 flap-lid radar, phased array, electronic beam steering, later the S-400, even more advanced, S-500 in development, all utilize phased array principles based on the German concept. China developed its own systems, the HQ-9 air defense, the Type 346 AESA radar for destroyers. Type 052D and Type 055 warships have phased array radars similar to AEGIS. China studied Soviet technology, which in turn was based on German foundations. The line leads back to Germany, even if it passed through Russia. And now we come to modern AESA radars. Active electronically scanned array. The next evolutionary step. Instead of passive phase shifters, each array element has its own transmitter, receiver, fully digital control, each module independently controlled. This allows for extreme flexibility. The beam can handle multiple targets simultaneously. Different wavelengths for different functions, adaptive beamforming against jammers, low probability of intercept modes. AESA is the current state of the art. The F-22 Raptor has the APG-77 AESA radar. The F-35 has the APG-81. The Eurofighter Typhoon gets the Captor E, developed by a consortium including Hensoldt. The Rafale has the RBE-2AA. The Gripen E has the Raven ES-05. Every modern fighter jet under development gets AESA radar. Why? Because it's superior. Better performance, better reliability, better flexibility, and they all are based on phased array technology. And phased array came from Mammut, and Mammut came from GEMA, Germany in 1943. Let's talk about the economic dimension. The global radar industry, over $50 billion annually. Military radars account for about half, civil radars the other half. Companies like Raytheon, Lockheed Martin, Northrop Grumman, Thales, Leonardo, Hensoldt, BAE Systems, all build radar systems. Thousands of engineers, hundreds of billions of dollars invested over decades. And the fundamental principles? Heinrich Hertz's electromagnetic waves, Chris Hill's early radar device, GEMA, Telefunken pulsed precision radars, Mammut phased array, all German, no licensing fees. That knowledge was taken as spoils of war, made public domain, used by the entire world. Germany itself now buys radar systems. Hensoldt supplies AESA radars for Eurofighters, TRML 4D mobile air defense, GESTRA space radar for space surveillance. These systems are technologically advanced. Hensoldt is a leading company, but the foundations come from Telefunken and GEMA from 80 years ago. Germany pays billions for defense systems that are conceptually based on its own inventions. The irony is obvious. Consider the civilian applications. Air traffic control. Every airport worldwide uses radar for aircraft tracking. Weather forecasting. Doppler radar shows precipitation and storm formation. Ship navigation. Every major ship has navigation radar. Speed measurement. Police use radar for traffic control. Automotive industry. Modern cars have radar for adaptive cruise control, collision avoidance, lane change assist. All these applications use radar principles. All these principles lead back to German research and development. Now, I want to ask directly, if you find this technical documentation valuable, if you appreciate me bringing 138 years of history, from Hertz to Hensoldt, into a clear line, if you want this channel to continue producing such detailed research, use the Super Thanks feature. This story isn't just the past. It's active in every radar worldwide. Air traffic control that lets you travel safely. Weather forecasting that warns you. Air defense that protects nations. Understanding the origins is essential, and that research takes time and effort. Your support makes more of it possible. Back to the technical history. There's an interesting question. Why did German engineers and scientists so dominate early radar development? Several factors played a role. First, the strong scientific tradition. Germany had a thriving physics community in the late 19th and early 20th centuries. Hertz was just one of many brilliant German physicists. Max Planck, Albert Einstein, Werner Heisenberg, Max Born. Germany churned out Nobel laureates. This robust scientific culture fostered innovation, pushing boundaries and encouraging exploration. Second, the robust industrial base. Siemens, AEG, Telefunken. The German electronics industry led the world in the 1920s and 1930s. They possessed cutting-edge expertise in high-frequency technology, vacuum tubes, and precision mechanics. When radar became strategically important, they had the established infrastructure and the technical ability to build it. Third, massive military investment. Hitler wanted technological superiority. Radar received unprecedented funding. The best scientists were recruited. The best factories were allocated resources. Wartime priorities meant unlimited resources were available, accelerating development at an astounding rate. This unwavering commitment provided the fertile ground for groundbreaking advancements. Fourth, fierce competition between companies. GEMA, the Society for Electroacoustic and Mechanical Devices, Telefunken, Lorenz. They aggressively competed for Wehrmacht contracts. This intense competition fueled innovation. Each company strived to outdo the others. The result? Rapid technological progress, a relentless pursuit of excellence. These factors combined to explain why Germany possessed the world's best radar technology by 1940. But technological superiority alone doesn't win wars. Germany had better radar, but less industrial capacity than the Allies. America produced more radar units, even if individually they were less sophisticated. Quantity has its own quality. Germany simply couldn't compete with Allied mass production. But after the war, when the victors absorbed German knowledge and combined it with their own industrial capacity, something truly powerful emerged. American production plus German design equaled global dominance. This is precisely what happened with radar and with many other technologies: rockets, jet engines, submersibles, night vision devices. It was always the same pattern. Now, let's jump ahead to 2025. Hensoldt AESA radar for the Eurofighter, the Captor E. The consortium, including Hensoldt, Leonardo and Indra, has developed a state-of-the-art system. featuring 1400 transmitter-receiver modules, electronic beam steering in microseconds, multi-target tracking, a low probability of intercept, and electronic warfare capabilities. This represents the cutting edge in 2025. But look at the fundamental principles. Phased array with electronic beam steering. That's the Mammut system of 1943, further evolved over 82 years. Consider GESTRA, a space radar developed for the German Space Situational Awareness Center. It's one of the most advanced radars in the world for space surveillance. It will track satellites and space debris, providing collision warnings and re-entry predictions, offering extremely precise orbit tracking. The technology is undeniably cutting edge, but the foundations? Pulsed radar with precision tracking, Würzburg principles applied to space. Then there's the TRML-4D, a mobile air defense radar developed by Hensoldt. Currently in active service with the Bundeswehr, it offers 3D target acquisition, digital beamforming, and 360-degree coverage, capable of detecting and tracking drones, cruise missiles, and aircraft. Germany can now produce 30 TRML-4D radars per year. Demand is soaring due to the conflict in Ukraine. Modern air defense requires modern radar systems, and Germany is delivering them. Based on technology that Germany pioneered 80 years ago, that completes the circle. Germany develops radar from 1887 to 1945. Germany loses the war. Its technology is seized. The world continues to develop radar based on German knowledge. And by 2025, Germany is purchasing highly advanced radar systems, but the fundamentals are still German. Hertz's electromagnetic waves, Hülsmeyer's early radar device, GEMA, Telefunken Würzburg and Freya systems, the Mammut phased array. All of this lives on in every modern radar system. Consider the global influence. Every country with an air force uses radar. Every country with a navy uses radar. Every country with air defenses uses radar. Aircraft, ships, ground stations, tens of thousands of radar systems worldwide, both military and civilian, all based on principles developed in Germany between 1887 and 1945. This represents a technological influence of unprecedented scale, and no one pays royalties. The knowledge was seized as war booty. After World War II, there were no patent rights for Axis powers technology. The victors were free to exploit what they captured. From a legal standpoint, this was legitimate. War law, reparations, the winner takes all. From a technological history perspective, it represents one of the greatest knowledge transfers in history. Hundreds of German patents, thousands of technical documents, dozens of leading scientists. All were internationalized, becoming the foundation of global industries. The human dimension is complex. Bill Runge, Telefunken's director who developed the Würzburg system, was interviewed and then largely forgotten. Rudi Kohler, the father of German radar at GEMA, the Society for Electroacoustic and Mechanical Devices, died in obscurity. The engineers who built the Mammut system appear in no history books. Their names are unknown. But their work lives on in every AEGIS-equipped ship, every Patriot missile system, and every modern fighter jet. Technology outlives its creators. But should history forget them? Heinrich Hertz died in 1894, at the young age of 36. He never saw the applications of his discoveries. No radio, no radar, no microwaves, nothing. He was a pure scientist, motivated by curiosity about the nature of the universe. But his legacy is immense. Without Hertz, no radar. Without radar, no modern aviation, no space exploration, no accurate weather forecasting, no effective air defense. One man, 36 years old, permanently changed the world. Chris Hill died in 1957. He lived through World War II. He witnessed radar become decisive. He saw how his idea from 1904 became the basis for military systems. But he never received proper recognition. No Nobel Prize, no millions from patents that had long expired. He died as a forgotten inventor. But in 2025, 68 years after his death, the world utilizes his idea every single day. This is often the fate of pioneers. They are too early. The world isn't ready. They pass away before their ideas triumph, but the ideas survive. And sometimes, decades later, the idea transforms the world. Chris Hill in 1904. The early radar device is rejected. 2025. Every ship has radar. The irony is both bitter and beautiful. Let's summarize the technical evolution. 1887. Hertz proves the existence of electromagnetic waves. 1904. Hülsmeyer demonstrates the radar concept. The 1920s. Pulsed radar is developed. 1935. GEMA, the Society for Electroacoustic and Mechanical Devices, along with Telefunken, begin development of military systems. 1940. The Würzburg radar system becomes operational, achieving an accuracy of 25 meters. 1943. The Mammut, or Mammoth, represents the first phased array radar. 1945. The technology is seized and globalized. The 1960s and 70s witnessed the emergence of the first large phased arrays, such as AEGIS and Patriot. The 1990s and 2000s see AESA become the standard. By 2025, Hensoldt, with its GESTRA system, offers the most advanced systems, yet still based on German foundations, 138 years from Hertz to Hensoldt. That's the documented lineage. The technical genealogy is clear. Every modern radar system is a technological descendant of German innovation. Is this a tribute to German engineering prowess, or is it systematic appropriation? The answer, it seems, depends entirely on your perspective. Historically, victors take spoils of war. This has been commonplace for millennia. Germany lost and paid with technology. Technologically, good ideas spread. This is the natural course of evolution. Economically, Germany spends billions on systems based on its own prior knowledge. The irony is profound. Morally, should inventors receive recognition, even posthumously, or is technology the common heritage of humanity? These questions don't have easy answers. But the facts are clear. Every radar worldwide uses principles developed in Germany, from airport radar to missile defense, from weather radar to automotive collision avoidance, from ship navigation to space surveillance. Radar is everywhere. German technical DNA is everywhere. Now you know the full story. 138 years. From Hertz in Karlsruhe to Hensoldt in 2025, from theoretical physics to a global industry, from one man in a lab to tens of thousands of systems worldwide. The lineage is documented, the technology is universal, the legacy is permanent. So, here's a final question for the comments. Is this technological evolution or systematic appropriation? Germany invented the foundations of radar. Germany lost the war. The Allies took the technology, developed it further, and now sell it back to Germany. Fair, unfair, the normal course of history, or should there be recognition, perhaps even compensation? Write your opinion in the comments. This question doesn't only apply to radar, it affects hundreds of technologies. Rockets, jet engines, computers, torpedoes, night vision devices, all followed the same pattern. All are global today. All have German roots. How should history deal with this? I've given you the facts. The technical lineage is documented. The numbers are real. The connection from 1887 to 2025 is undisputed. What you conclude is your decision. But now you know. The next time you see an airplane tracked by radar, when you hear a weather forecast based on radar, when you read about Patriot missiles in Ukraine, AEGIS ships in the Pacific, F-35 fighter jets, all use radar. And all that radar is based on German knowledge. Heinrich Hertz, Chris Hill, GEMA, Telefunken Würzburg, Freya, Mammut, names that no one knows, but technologies that everyone uses. This is the story that no one tells until now.